Hi everybody, I hope this video finds you well. In today's video, we're going to be moving on into the last chapter of our course, which is chapter 9 from your textbook. To do this, we're going to be starting by our discussion with section 9.1, which introduces you guys to what we're going to be discussing in this chapter, which is namely systems of differential equations. But we're going to be focused on a very particular type of system of differential equations, which shouldn't be too much of a surprise, is going to be called a linear system of differential equations. So let's discuss what a linear system of differential equations really looks like. So, a linear system of differential equations is a system of differential equations that fits this format. Now, this is a lot to sort of unpack here, so let's talk a little bit about some of the things going on before we go ahead and jump into what the details of this definition actually are. First of all, when we're working with standard differential equations, right, we normally think about them with the dependent variable being denoted with y and the independent variable as x. When we're working on systems of differential equations, we change that a little bit. For systems of differential equations, we will be letting x1, x2 through xn represent the n different dependent variables that we'll be working with. And we'll let the variable t represent the single independent variable that determines all of the dependent ones. A system of differential equations, then, is a system of n equations that tells us about the derivative of each of the dependent variables. So you'll notice that in this system, each equation relates to one of the derivatives. This one tells us about the derivative of our first dependent variable. This one tells us about the derivative of our second dependent variable, all the way down to the last one, which tells us about the derivative of our last independent variable. That means that if we have n dependent variables, a system of linear differential equations is going to have n different equations. Then, what do we have on the right-hand side here? Well, what you're going to notice is that each of the derivatives is going to be a linear combination of the other dependent variables. The coefficients here are allowed to be functions of the independent. That's very similar to what we learned about when we learned about linear differential equations. We said we can't have any functions of the dependent variable y, but we are allowed to have functions of the independent variable. Here, the independent variable is going to be t, so our coefficients are going to be functions like a11 of t, a12 of t, down to a1n of t, and then so on, a21 of t, a22 of t, a2n of t, so on. What is this last component here with this b1 of t, b2 of t through bn of t? Well, if those guys don't show up, then what we're basically saying is that we have these differential equations where if we put everything onto the other side, we'd have a standard sort of linear format and it would be equal to this b1, b2 through bn. So if those b1, b2 through bn are all equal to 0, then we call the system homogeneous. If these b1 through b2 through bn, some of those are not 0, then we call this non-homogeneous. So we use that sort of standard language of homogeneous and non-homogeneous based on these sort of solution elements of the system. Now, you can imagine that as we sort of do this investigation a little bit further, this is prime sort of material to rewrite into a vector equation. We could think about this as a column vector of derivatives. We could think about this component as a matrix multiplication of a matrix of these a11 functions through a1n through an1, ann, times a vector function of that x1, x2 through xn, plus that vector b1 down to bn. Now, that's what we're going to be doing in section 9.2 is understanding how to rethink about this in terms of a vector formulation. But I just wanted you guys to sort of realize that is where we are headed here. Now, what does it mean to come up with a solution to a system of differential equations? Well, that means you need to figure out what x1, x2, and xn should all be. What are those functions in terms of our independent variable t? So, a solution to this type of system is an ordered n-tuple of functions x1 of t, x2 of t, through xn of t that makes this system true for all values of t. Now, like I said, eventually, right now we're going to think about this as an ordered n-tuple of functions, but eventually we're going to think about these as a vector function. We can think about the solution as a column vector where the elements of that column vector are functions, not just values, but actual functions. So that's eventually what we're going to be headed to in section 9.2. So what are we going to do in the remainder of this video? Well, I'd like to give you guys one example of actually looking at a system like this and actually seeing sort of a basic way of solving the system. Now, our basic way is not going to be an ideal route. We're going to see it's a little bit messy, and we'll learn a much better way based on some of the things you guys have already learned in this course in a couple later videos. So we'll take a look, though, at one basic example. Then we'll also talk a little bit about some situations that can be modeled using systems of differential equations to sort of motivate us about why we want to even bother studying systems of differential equations. So let's get into that example and then talk a little bit about the modeling applications. All right. So this is going to be our first attempt at solving these systems. And like I said, by the time we get to like section 9.4, 9.5, we're going to learn a much more sort of computationally efficient way of solving these systems. But for now, let's see if we can come up with some sort of direct approach. All right, so here's an example system. We have x1 prime equals 3x1 plus x2, and x2 prime is supposed to be 2x1 plus 4x2. Notice that this is exactly what this definition is saying here. We've got two dependent variables here, x1 and x2, and then two equations, one that tells us about the derivative of x1, one that tells us about the derivative of x2. Now, this is a condensed notation. You notice that we're not writing the of t. Technically, we could have written the first equation as x1 prime of t is 3x1 of t plus x2 of t, but we sort of condensed the notation remembering that x1 and x2 are actually functions of t here. Would this system be homogeneous or non-homogeneous? Well, notice that this is 3x1 plus x2, and then the b1 of t in our previous would be 0, and this guy is also plus 0. So this is a homogeneous system here. So this is an example of a homogeneous system. What would it look like if it was non-homogeneous? Well, it would be something like x1 prime, so x1 prime equals 3x1 plus x2 plus t. That would be non-homogeneous because of that plus t. Or if this guy was x2 prime equals 2x1 plus 4x2 plus 5. If it has that plus 5, that would make it non-homogeneous. Okay, so let's think about how we could actually try to play around and solve this thing. So what we're going to do is we're going to write it, since we know that it's homogeneous, as equal to 0. So let's bring everything over onto one side. So we can write this as x1 prime minus 3x1 minus x2 is equal to 0. And then on the second equation, we can call it minus 2x1, just trying to keep things lined up there, plus x2 prime minus 4x2 is equal to 0. That's just shifting everything, getting it equal to 0. And also notice that that connects this definition of homogeneous system to the original sort of definition of homogeneous that where we said we had it equal to 0. Okay, now, we also have that nice differential operator notation, so let's write that to help understand this a little bit better. So let's review this as d minus 3 of x1. d minus 3 of x1 is exactly equivalent to the derivative of x1 minus 3x1. And then minus x2 equals 0. Just a nice way of sort of viewing it. Now remember that the differential operator here, d, would be the derivative with respect to our new independent variable, t. Down here, we can do the same sort of thing. We can view this as minus 2x1 plus d minus 4 applied to x2. And that's equal to 0. And again, d minus 4 of x2 would be the derivative of x2 minus 4x2. All right, now, what can we do with this? Well, in general, when you guys first learned about solving systems of linear equations, not linear differential equations, but just linear equations, you learned methods like substitution and elimination. So let's see if we can do our standard sort of elimination. Let's see if we can sort of use this guy to clear this out so that we can get a differential equation that only has one dependent variable, because that's pretty much what we've studied in this course. So up top here, let's multiply this equation by 2. So if we multiply the top equation by 2, we get 2d minus 3 of x1 minus 2x2 is equal to 0. What should we do on the bottom equation? Well, to make this match this, we would need the operator d minus 3. So let's apply the operator d minus 3 to both sides of this equation, which of course is a valid operation. Now remember though, you guys know that the differential operators are linear, meaning that if we apply d minus 3 to this whole equation, it'll distribute over this addition and apply to this and this separately. You also know, since it's a linear transformation, that when you apply it to 0, it automatically outputs 0. So if we do that, we would get negative 2 d minus 3 of x1 plus d minus 3 d minus 4 of x2 equals 0. Now, with this, we can go ahead and use standard elimination and add these equations together. So let's go ahead and do that. So we're going to add these equations together. Notice that these components are just going to drop out. So what do we get as a result then? Well, we're going to get minus 2x2 and then plus d minus 3, d minus 4, x2 equals 0. Now, it might not be immediately clear why this is a lot better, but this is. Right? Now, this is a differential equation with only one dependent variable. Normally, we're used to this guy being a y, but it's that's just changing letters. So we know how to solve this. If we rewrite this a little bit, this is minus 2x2 plus d squared minus 7d plus 12 of x2. And if we bring that minus 2 in here, then that 12 is going to become a 10. So this is really d squared minus 7d plus 10 of x2 equals 0. Well, this should feel very comfortable, very familiar here, right? This is constant coefficient, homogeneous differential equation. We know how to solve this very easily. We can factor d minus 5, d minus 2, x2 equals 0, giving us two roots, r equals 5 and r equals 2. This guy is multiplicity 1. This guy is multiplicity 1. So we get that x2 is c1e. Now we should be careful here. Remember, our independent variable is now t. It should be c1e to the 5t plus c2e to the 2t. So there we go. We now know what the x2 dependent variable should look like. The x2 is the function c1e to the 5t plus c2e to the 2t. Now we got to go find x1. How do we normally find the next variable after using elimination? Well, we need to substitute this back in to one of the equations and find x1. Let's think about which equation would be easier to do. Well, we've got two options. So let's just think about the ones back here. If we plug it into here, we'll know x2, and then we'll have an equation that involves x1 prime and x1. Unfortunately, that would be a differential equation, which certainly we're not afraid of solving. I mean, we've spent a lot of time in this class solving differential equations, but this would be a differential equation to solve for x1 if we plug in for x2. What if we plug into this guy, though? Well, we'll know x2. We should be able to take the derivative of x2, and then we'll just have an algebraic equation for x1, because this isn't x1 prime. It's just x1. So we want to plug it into this second equation here. So we're going to take this guy here, and we're going to bring this up here, and we're going to plug into that equation 2. So let's plug into equation 2. So what is that going to look like? Well, it's going to be minus 2x1 plus the derivative of x2. But we just figured out x2 is c1e to the 5t plus c2e to the 2t. And then minus 4 times x2, so this is prime there, excuse me, and then c1e to the 5t plus c2e to the 2t, and that's supposed to equal 0. Now, applying this derivative is easy. We can just go ahead and do that, and we can also distribute in that minus 4. So we get minus 2x1 plus 5c1e to the 5t plus 2c2e to the 2t minus 4c1e to the 5t minus 4c2e to the 2t. And that's supposed to equal 0. Now let's combine some like terms. We get minus 2x1, 5c1e to the 5t, and minus 4c1e to the 5t. Should give us plus c1e to the 5t. And then we should get minus 2c2e to the 2t equals 0. Then, of course, we can say that that's c1e to the 5t minus 2c2e to the 2t equals 2x1. And that looks like x1 then is 1/2 c1e to the 5t minus c2e to the 2t. And there we go. We now know what x1 as a function of our independent variable t should look like. And, of course, we know what x2 is. So how could we actually say our solution? We could say our solution is x1 equals 1/2 c1 e to the 5t minus c2e to the 2t, and x2 is c1 e to the 5t plus c2 e to the 2t. There we go. Now, like I mentioned, in our next video, in section 9.2, we're going to learn how to formulate this as a vector. So let's think about this guy as a vector function. Instead of saying x1 and x2, let's think about this as x of t, and let's treat this as a vector function, 1/2 c1 e to the 5t minus c2 e to the 2t, and then the second element is going to be c1 e to the 5t plus c2 e to the 2t. Okay. That would be an alternate way of phrasing. Instead of saying that we have two separate solutions, we could think about it as a vector. You guys are comfortable that when we learned about solving systems of linear equations, we said you could just say what x, y, z all equal, or you could phrase it as a vector. But I want to look a little bit more at this vector. Let's split this apart into the components that involve the e to the 5t and the e to the 2t. Notice that I could view this as the sum of two vectors. 1/2 c1 e to the 5t and c1 e to the 5t plus negative c2 e to the 2t, c2 e to the 2t. And then notice I could do a little bit of factoring, c1 e to the 5t and c2 e to the 2t. Okay, so we can view this as c1 e to the 5t 1/2 and 1 plus c2 e to the 2t minus 1 and 1. Okay. Now you might be saying to yourself, okay, sure, I agree algebraically, not sure exactly why I care. Well, this is going to hint at what the general method for this type of system is going to be. When we get into section 9.4 and 9.5, we're going to learn a much faster way for solving these systems rather than this sort of brute force approach. And what it's going to be based on is it's going to be based on eigenvalues and eigenvectors. If you guys want, on your own, take a look at this system and think about the sort of coefficient matrix here. The coefficient matrix here would be 3, 1, 2, 4. If you want, on your own, take a look at the eigenvalues and eigenvectors of that matrix, 3, 1, 2, 4. What you will find is that the eigenvalues of that matrix, 3, 1, 2, 4, the eigenvalues are 5 and 2. Well, notice that we get an e to the 5t and an e to the 2t. Not a coincidence. What you will also find is that for the eigenvalue of 5, an eigenvector is 1/2 1. And for the eigenvalue of 2, an eigenvector is negative 1, 1. Which tells you that in general, the way we're going to solve these systems is that we're going to find the eigenvalues and their corresponding eigenvectors and use those to build the general solution. Now, we're not quite there yet. We've got a couple things to develop along the way, but that is where we are headed here. Okay, last thing I want to do in this, since this is just an introduction to systems here, is talk briefly about why systems are important and the types of things we can model with them. So let's take a look at one sort of differential modeling example based around a system. So, why are systems important? Well, one of the most famous sort of basic uses of systems of differential equations for modeling is in studying populations that relate to one another. And probably the most classic example of this are what are called predator-prey models. So let's take a look at a little example of this. So, we're going to suppose you're studying two populations of animals. The first population, P1, is a prey animal. And the second population, P2, is a predator animal. So again, we're keeping things very basic here. We're saying that we've only got these two populations that interact. P1, the prey, and P2, the predators. So we're going to suppose that the prey animal's population grows proportionally to the product of the current population and the difference between the current population and the carrying capacity, which is 5,000. This is pretty standard. We did this way back in chapter 1. We actually called this the logistic growth model, right? This logistic growth model basically says that your population grows according to some proportionality to how many there currently are, but also how different your current population is from the max population, which we call the carrying capacity. However, since we're modeling two populations here, we're going to further suppose that the prey animal's population decreases proportionally to the predator population. So the more predators there are, the more quickly the prey population decreases. That should make sense because the predators are eating that prey. All right, we're going to suppose also that the predator's population grows proportionally to the current population of prey. Now, this is a little bit interesting of an assumption. This is saying that the predators don't necessarily grow proportional to their own population, but instead to the current population of prey. So that could mean that the predators are coming into the area, right, because there's more prey. But in other words, we're saying the more prey there are, the more predators there will be. So let's write down a system of differential equations to model these two populations. So we would say that dp1 dt. So how does the first population change? Well, it apparently grows proportionally to the product of the current population and the difference between the current population and carrying capacity. So we'll use a constant proportionality, K1, times P1, that's the current population, and then the difference, 5,000, minus P1. So we would be saying this is just the standard sort of logistic growth model. But we know that it also decreases proportionally to the predator population. So we'd use a new constant of proportionality. We do minus, since it's decreasing, K2 times P2. And notice that this right here would be a system, right? Because we're saying the change in that first population is based not only on the first population, but also the second population. All right, what about the second one? Well, we'd say dp2 dt. Well, the predator's population grows proportionally just to the current population of the prey. So we use a third constant proportionality. Population of the prey, that's P1. So we'd have this system of differential equations. Now, this is a pretty simple system of differential equations, but it actually would not be a linear system. Because if you think about this, if you actually expand this out, you would get a P1 squared. So you'd have a function of a dependent variable. So this would actually be an example of a system of non-linear differential equations. And you can imagine that the behaviors of this could be pretty complex. As P1 starts to go up, if P1's population is large, well, then that means that P2 is going to increase, because the more prey there are, the more predators there are. But the more predators there are, well, that means that the population of prey is going to start to decline. If the population of prey starts to decline, well, then the predator population might start to decline, or at least its growth will slow. So there'll sort of be a varying of back and forth in terms of what is going to actually happen with these populations. Now, this is only one example of a simple predator-prey sort of model, and we'll take a look at some other ones as we start to learn how to solve these systems. But I just wanted you guys to sort of see an application of systems of differential equations, and also to just remind ourselves a little bit about modeling with differential equations. In our next video, we'll have a very quick discussion of how to formulate all of this in terms of a vector equation rather than a full system, and then we'll be ready to actually move on, talk about how we're going to solve these things using eigenvalues and eigenvectors as a sort of better computational approach.